source of 230 volts as well as 50 Hz frequency, and series resistance to avoid the errors. We have given 1 milliohm, and measurements branch voltage and current. This is the current measurement which is in series with the line. This is the line current, and THD. THD in the total current waveform is measured with THD block and display. In display it is THD content was displayed, and here there are two legs. The first leg is TSC, so capacitance value 0.3 e power minus 4, and anti-parallel combination of thyristors are connected in series. So first one, so amplitude you can take 1 or 10 whatever, period it should be 1 by 50, so 0.02 seconds or 20 milliseconds. So pulse width percentage of the period 50, and phase delay 0.02 into, so firing is at 90 degrees. Let us take that. You can also change the firing angle. Switch on time. 10.02, 90 plus 180. So this is the TSC black. TSC black, and second one is TCR black. In the TCR black, inductance 3 milliohm, 3 milli in this, and this is the amplitude 10, time period 0.0 to 20 milliseconds, 50 pulse width 50, phase delay 0.02 into 0.02 into 120 is the delay angle alpha. 10.02, 50, 0.02 into 120 plus 180 by, so alpha plus 180 second thyristor. So this is the firing of TCR, and this is the current flowing through the TCR, current measurement block, THD content of TCR current, and this is the bus voltage. At any point voltage is seen, so bus voltage is measured here. Okay, now simulation time 0.1 seconds, and power GUI black discrete. You can change this also, 5 into 10 power minus 6, and you can simulate this one. Now you will get the blue color is the voltage waveform, red color is current waveform of TCR, which is same as that of the FCTCR type and TCR. Wherever it is there in that block, you have high TCR, that current is controlled, delay angle controlled. So this is the waveform. Okay, this is the TCR current waveform, and THD content is 47.52%. and this is the total current. This is the waveform of total current. Summation of IC and ITCR. And THD content is 121.8%. This is 0.3. Let us look at this figure with a different value. Now 47.52. This waveform is same. This waveform is changed now. Therefore, the content is 47.6. Okay. Let us change this one. 0.8. 47.58. This is the waveform. This is the current waveform. By changing the value of FC, you can get the different waveforms and THD ratings, THD values. Very high. This is very high. So, you can also try with the exact design. I think you can design based on your reactive power requirements. So like this, you can do the TSC, single phase TSC TCR type SVC with different ratings. And with different firing angles also you can try. Now 3-phase TSC TCR type SVC. Now let us look at the figure. This is a 3-phase programmable voltage source of 14 volts and 50 Hz. So this is the swing bus, slack bus. This is the resistance common value 1 milli ohm. So this is the TSC 0.4 into 10 e power minus 4 capacitance, and first leg, second leg, third leg of TSC. Each leg will have 90 degrees, 180, plus 90. So 90 plus 120, 90 plus 120 plus 180, 90 plus 240, 90 plus 240 plus 180. This is the switching pattern of TSC. Now this is the TCR, 3 into e power minus 3. So 3 phases, 3 legs. In one of the phases, ammeter is connected, current measurement. This is ITCR. ITCR. And other two legs are connected with the anti-parallel combination of thyristors. This is 120, delay angle 120, 120 plus 180. You can go for other firing angle also. This is 240, 120 plus 120, 240, 240 plus 180, 240 plus 120, 120 plus 120 plus 120, or 240 plus 120. And this is 240 plus 120 plus 180. This is the firing of TCR, and the voltmeter is connected here, voltage measurement. This is the total current, which is connected in series with the line. Now let us simulate this. 48.7% is the THD content of TCR. Yellow color is the voltage, and blue color is current. This is the yellow and red. Yellow is the voltage waveform, red is the current waveform of TCR. Even it is a 3-phase, in all 3 phases you will get similar kind of waveforms of TCR. Then the THD is 48.7. This is the total current. This is the waveform of total current, which is similar to the previous one. And this is 69.6% is the THD content. You can go for 5. This is the current waveform, total current. This is the I total of 3-phase TSC TCR type SVC. Now this is a figure, 3-phase source, series resistance, TSC, TCR, and corresponding measurements. This is the TSC TCR type SVC. Now, this is the course project. By using TSC TCR type SVC, you need to control the terminal voltage of transmission system with pi model, I'm showing with the pi model. You can also do it with distributed line. I think this is course project number 9 or 10. I don't know exactly. And you can complete all course projects. Plenty of time is there to complete the course projects. So let us look at this figure. So this is the three-phase programmable source of 381 kV line to line voltage. So 230 kV is the phase voltage, and load flow it is swing bus, reference bus. This is the RMS may not be required. You can also directly measure. In fact, power is average value. If you measure with RMS block, you need to divide with 1.1. So this is the power measurement. Inputs are three-phase power measurement, instantaneous. VABC and IABC can be taken as inputs. Outputs are P and Q, active power and reactive power respectively. So this is the series resistance three-phase 1 milli ohm. You can measure branch voltage and currents. So this is the three-phase measurement block. VABC and IABC are the voltages and currents in three-phase. Now this three-phase voltage using Pmax, you can divide into 3 VA, VB, VC. You can connect the scope so that you can get the voltage waveforms separately per phase voltages. And this is the RMS block in one phase, phase A, and this is the display to measure the RMS value of the phase voltage. Actually 230 kV, so we get 229 here. We'll see later that this is the display RMS block. This is the pi line model. The data is given from the Kundu textbook, 230 kV. The frequency was changed 50 Hz. So this is the positive resistance and zero sequence. Positive sequence and zero sequence resistances, reactances and capacitances. Line length is taken as 400 kilometers. This is the pi line model. So at the receiving end, you have three-phase measurement block, VABC and IABC. I have not taken the current measurement here. If you want, you can take that. So this is the VABC. Dmax is used to get the VABC, and this is RMS measurement. So this is the receiving end voltage and sending end voltage waveforms. And now let us go to load. This is the load. Three-phase breaker is used here. It is normally open. It is closed at first cycle and opens at 5000 cycles. So in the steady state, you will get these values. So therefore, it is closed. And the RL circuit, this is the nominal frequency, voltage, nominal phase-to-phase voltage, 220 kV. 220 into root 2, you will get some peak value. So this is the frequency 50 Hz, active power is 100 kilowatts, reactive power 100 kVAR. Capacitive reactive power is 0. And measurements, branch voltage and currents. Okay. So this is the load. Coming to TSC, three-phase TSC TCR type SVC. Here this is the TSC which is connected to the receiving end. This three-phase breaker is there, normally open and it is closed at 1 and open at 5000. Therefore, it is closed. It is in the circuit. Three-phase TSC 1 into e power minus 6. Band voltage and currents here. These are the three legs of phases A, B, C. And 35 degrees is the firing angle. You can take other angle also. There is no problem. 35 plus 180. And the second leg 35 plus 120. 35 plus 120 plus 180. Here third leg 35 plus 240. 35 plus 240 plus 180. So this is the firing of TSC. And coming to the TCR, this is also three-phase breaker. Normally open. It is closed at 1 and open at 5000. Therefore, it is in the circuit. Measurements, breaker voltage and currents. A, B, C, three legs. Each leg, let us look at the firing. 35. We can also take different value. Here also 35 plus 180. 35 plus 120. 35 plus 120 plus 180. Second leg, third leg, 35 plus 240. 35 plus 240 plus 180. So this is the TCR and its firing. So this is the entire circuit. So this is the source, series resistance, transmission line, receiving in load, and this is the three-phase TSC TCR type SVC. TSC TCR type SVC. Okay. Now you can simulate this. Let us simulate this. Now sending end voltage RMS value 229, receiving end 229. So both are equal. Small deviation you can neglect that, and you can measure the receiving and sending end voltages. Here receiving end voltage have some harmonics introduced due to TCR. Sending end, this is the pure sine wave. So therefore, the voltage may be same at both the ends. You can design a filter, or you can reduce the harmonics with the help of sequential switching. That you can extend that work as a mini project, and you can write the paper to publish. So this is the TSC TCR type SVC course project. Voltage control of the transmission system with load variation using TSC TCR type SVC. Okay, now you can do your simulations and show me.